Campi Flegrei is still moving, and for the people living around Pozzuoli and western Naples, the signs are impossible to dismiss. Earthquakes continue beneath the caldera, the ground remains elevated, and volcanic gases continue escaping through the hydrothermal system. The activity rises and falls from week to week, but the larger pattern has persisted for years. Recent monitoring reports from the Vesuvian Observatory continue to document seismicity alongside significant ground deformation, with the latest available reports maintaining an average uplift rate of approximately 10 millimeters per month, or about 4/10 of an inch. That movement is almost invisible from the street, yet over months and years it becomes a major geological signal. The crucial point is that Campi Flegrei remains restless, but the current evidence does not indicate that a catastrophic eruption is imminent. Then, on July 31st, the pattern changed dramatically. A magnitude 4.7 earthquake struck the Campi Flegrei area west of Naples at around 7:46 in the evening local time, becoming one of the strongest earthquakes recorded in the region during the modern period of unrest. The earthquake was extremely shallow at roughly 3 kilometers, or about 1.9 miles beneath the surface, which made the shaking especially intense across nearby communities. Residents rushed into the streets as buildings shook, while the earthquake caused damage to structures and infrastructure, power disruptions and interruptions to local transport. Several dozen people were reported injured, and hundreds of residents were temporarily evacuated from buildings considered unsafe. The earthquake was followed by numerous smaller tremors, including additional felt events, keeping the region unsettled long after the main shock had passed. The latest monitoring picture also reinforces why residents can feel the unrest so strongly. Many of the earthquakes occur at shallow depths, sometimes only a few kilometers below the surface. A moderate earthquake generated close to a city can feel much more intense than an earthquake of similar magnitude occurring deep underground or far away. During the current period of unrest, earthquakes have repeatedly concentrated beneath the Pozzuoli area, Solfatara, Pisciarelli, Agnano, Bagnoli, and surrounding parts of the caldera. Yet the earthquakes are only one part of the picture. The most persistent signal is the continuing deformation of the ground. Campi Flegrei has been experiencing a prolonged period of uplift since 2005, and scientists have linked this deformation closely with the increasing seismicity. Recent research published in Communications, Earth and Environment in February 2026 found that the long-term earthquake trend can be reproduced by models in which ground deformation loads faults and changes their tendency to rupture. In other words, the earthquakes may be partly a mechanical response to the crust being pushed and deformed. The researchers also found that short-term earthquake clusters can be influenced by interactions between earthquakes themselves. This is important because it shows that a burst of seismic activity does not automatically require a sudden injection of magma. Some of the clustering can develop through the way stressed faults respond to one another. One of the most important discoveries of 2026 has come from looking much deeper than the earthquakes people can feel. In May, researchers published a study in Scientific Reports presenting what they describe as the first comprehensive three-dimensional geophysical image of the Campi Flegrei plumbing system extending down to approximately 50 kilometers or 31 miles. The study identified two major low-velocity zones. A shallower anomaly occurs around 10 kilometers, or roughly 6 miles, beneath the eastern part of the caldera. The researchers interpreted its shape as consistent with a localized zone of magma transfer or intrusion. Even more remarkable was a deeper anomaly beginning around 25 kilometers, or approximately 15.5 miles beneath the surface. The researchers estimated that this deeper zone could contain substantial melt, potentially representing a primitive magma source feeding the volcanic system from below. The discovery does not mean there is a gigantic underground lake of liquid magma sitting 25 kilometers below Naples. That interpretation would be misleading. A low-velocity zone is a region where seismic waves travel differently from surrounding material, and several physical conditions can produce such an anomaly, including high temperatures, partial melting, and fluids. In this case, the researchers interpreted the deeper feature as evidence consistent with a subcrustal primitive magma source. Their model suggests that Campi Flegrei's plumbing system extends much farther downward than surface observations alone could reveal. Above that deep source are other structures through which magma, heat, and volatile-rich fluids can move. The new imaging, therefore, provides a much more complicated picture than the familiar idea of one enormous chamber filling directly beneath the caldera. The same study identified something potentially important at around 10 kilometers or 6 miles depth. The shallow, low-velocity zone has a roughly vertical, elongated shape measuring several kilometers across, and the researchers suggested it may represent a localized region of magma transfer or intrusion. That is significant because it offers a possible connection between the deep volcanic system and the shallower crust where the present unrest is occurring. Magma does not necessarily have to rise as one continuous column. Instead, it can move through fractures, accumulate temporarily, release gases, and interact with surrounding rocks before continuing upward or stopping. Fluids can travel along some of the same pathways. The new seismic image therefore helps explain why Campi Flegrei can produce earthquakes and uplift at shallow levels, while the deeper volcanic system remains active many kilometers below the surface. Another major development this year concerns the hydrothermal system beneath the Pisciarelli area. A scientific report study published in April 2026 examined the complex network of hot fluids and gases beneath Pisciarelli and the neighboring Solfatara area. Researchers noted extremely high carbon dioxide emissions exceeding 600 tons per day in some measurements, together with persistent surface changes and frequent earthquakes. The study also highlighted a dramatic increase in seismicity since 2022. Approximately 18,000 earthquakes were recorded between January 2023 and August 2025, including the magnitude 4.6 event in June 2025. This combination of deformation, earthquakes, and intense degassing makes Pisciarelli one of the most important places for understanding what is happening beneath the caldera. The hydrothermal system is particularly important because it offers a possible explanation for some of the pressure changes observed at the surface. Deep volcanic heat can warm groundwater and produce steam and chemically altered fluids. Carbon dioxide and other volcanic gases can rise through fractures and interact with that circulating water. When pathways become blocked or pressure conditions change, fluids can accumulate and deform the surrounding rocks. The resulting pressure changes can trigger earthquakes without requiring a massive volume of fresh magma to rise toward the surface. This does not mean magma is irrelevant. The heat and gases ultimately originate from the deeper volcanic system, and magma-related processes may influence the hydrothermal circulation. But the distinction matters because it prevents every earthquake from being interpreted as direct evidence of magma breaking through the crust. Campi Flegrei's unrest can involve both magmatic and hydrothermal processes at the same time. The continuing activity at Pisciarelli also demonstrates why surface observations can sometimes be deceptive. A fumarole releasing steam and gases can look dramatically volcanic, but the visible emission is only the final expression of a much larger underground circulation system. Hot water moves through fractures, gas bubbles separate from fluids, pressure changes alter permeability. New cracks open while older pathways close. These changes can modify where gases escape at the surface. Researchers studying Pisciarelli have found evidence for progressive reactivation of the fumarole field since the early 2010s, making it one of the dominant degassing areas within the caldera. The system is therefore being watched not simply because it looks spectacular, but because changes in its behavior can reveal how pressure and fluids are moving beneath the surface. Meanwhile, scientists are developing new ways to identify hidden patterns in the earthquakes themselves. A scientific report study published in February 2026 used a combination of machine learning and statistical techniques to analyze seismic signals from Campi Flegrei. The researchers used a self-organizing map together with other signal processing methods to identify previously uncatalogued events and distinguish different types of seismic and volcanic signals. The system was also tested against independent data from early 2025. According to the study, the method detected changes in tremor and identified patterns preceding a major local earthquake with a magnitude around 4.4. This does not mean artificial intelligence can now predict Campi Flegrei eruptions. Instead, it demonstrates that automated systems may help scientists process enormous quantities of seismic data and recognize changes more quickly. That development could become increasingly valuable because the monitoring network produces far more information than a human team could comfortably examine one signal at a time. Every earthquake has a waveform. Every station records ground motion. Every deformation sensor adds another measurement. Satellites repeatedly scan the caldera. Gas instruments continuously measure emissions. Together, these systems produce a vast stream of information. Machine learning tools can search for relationships within that data, while scientists interpret the physical meaning. The goal is not to hand control of volcanic forecasting to an algorithm. It is to create another layer of detection that might reveal subtle transitions earlier. At Campi Flegrei, where the difference between an ordinary swarm and a meaningful change in volcanic behavior could be extremely important, faster recognition of unusual patterns could provide additional time for scientists and authorities to assess the situation. Another new study, published in April 2026, examined earthquake early warning at Campi Flegrei. The research focused on the possibility of providing extremely rapid alerts for local earthquakes, an especially difficult challenge because many earthquakes occur close to the communities exposed to the shaking. In a conventional earthquake warning system, the first seismic waves can be detected before the strongest waves arrive, creating a short window for automated responses. At Campi Flegrei, that window can be extremely small because earthquake sources may be only a few kilometers beneath the surface. Researchers therefore examined whether even a very short warning could help reduce impacts. The work demonstrates that volcanic unrest and earthquake hazard are connected but not identical. Even if a particular earthquake has no implication for an eruption, it can still damage vulnerable structures or cause injuries in a densely populated urban environment. Campi Flegrei is unquestionably restless, but the unrest is not simply a giant magma chamber filling toward the surface. Ground deformation, earthquake interactions, hydrothermal pressure, deep magma sources and shallow fluid movement can all contribute to what scientists observe. Some processes unfold over years, others occur within hours. An earthquake swarm can develop because faults are responding to long-term uplift. Gas emissions can change as fluids find new pathways. Deformation can continue even when the earthquake rate temporarily declines. Understanding which process is dominating at any given moment requires comparing multiple independent observations. That is why scientists resist dramatic conclusions based on one earthquake or 1 week of heightened activity. The historical record makes that caution even more important. Campi Flegrei has experienced major episodes of uplift and seismicity without producing an eruption. During the 1982 to 1984 crisis, the ground around Pozzuoli rose dramatically and thousands of earthquakes occurred. Yet the crisis eventually declined without a major eruption. Today's unrest is not necessarily following the same path, and the historical precedent cannot guarantee that the current episode will end quietly. But it demonstrates that deformation and earthquakes do not form a simple eruption countdown. The volcano can enter prolonged periods of instability and later return toward a quieter state. That possibility remains part of the scientific assessment today. The current unrest is serious enough to demand continuous monitoring, but the available evidence does not justify saying that an eruption is inevitable. The biggest concern comes from the population living directly above the volcanic system. Campi Flegrei's red zone contains roughly 500,000 people, while more than 800,000 additional residents are included in the yellow zone established for significant ashfall hazards. The numbers make Campi Flegrei unusual among the world's active volcanic regions. A major eruption would not occur in an empty wilderness. It would affect a densely developed metropolitan environment containing roads, railways, ports, hospitals, businesses, and critical infrastructure. Italy's civil protection authorities have therefore developed detailed emergency plans that establish evacuation zones and procedures. The existence of those plans should not be interpreted as evidence that authorities expect an eruption now. It reflects the opposite principle. Preparation must happen before a crisis, because waiting until an eruption begins would be far too late. The red zone is particularly important because it is designed around the possibility of pyroclastic flows, some of the most dangerous phenomena associated with explosive eruptions. These rapidly moving mixtures of hot gases, ash, and volcanic fragments can travel far faster than people can escape on foot. The yellow zone addresses a different threat, particularly the accumulation of volcanic ash that can disrupt transportation, damage infrastructure, and create problems for buildings and public health. These zones are planning tools, not forecasts. Their boundaries are based on scientific hazard assessments and emergency management requirements. At present, Campi Flegrei remains under the yellow volcanic alert level rather than a higher emergency stage. That status reflects continuing unrest, but does not indicate that authorities have declared an eruption imminent. The distinction is essential when interpreting the latest earthquakes and deformation. What scientists are watching now is whether several signals begin changing together. If uplift were to accelerate sharply, that would matter. If earthquakes became significantly more frequent or migrated into new parts of the volcanic system, that would matter. If seismicity began showing patterns consistent with rapid magma movement, concern could increase. Changes in volcanic gas composition or hydrothermal behavior could provide additional evidence. The key would be convergence. One measurement can be ambiguous. Several independent measurements changing in the same direction are much harder to dismiss. This is the foundation of modern volcano monitoring. Scientists are not waiting for one dramatic sign. They are searching for agreement among earthquakes, deformation, gases, thermal activity, and deep geophysical observations. This approach is especially important at Campi Flegrei because its underground plumbing system contains several interacting processes capable of producing similar surface signals. The February 2026 earthquake modeling study provides another reason to look beyond the raw earthquake count. Researchers found that long-term seismicity can be reproduced by the relationship between ground deformation and fault loading, while short-term clusters can partly arise through interactions between individual earthquakes. Their model was able to reproduce important features of the observed seismicity and produce probabilistic forecasts of earthquake rates and maximum magnitudes over weekly to monthly periods. This is not an eruption prediction system. It is a way of estimating how earthquake activity may behave under changing deformation conditions. The distinction is important because residents may see a sudden swarm and assume it represents an accelerating volcanic eruption. The latest science suggests that at least some of these short-term bursts can emerge naturally from the mechanical interaction of faults under a long-term process of uplift. Perhaps the most striking recent development is therefore not an earthquake at all. It is the growing ability to see the architecture responsible for the earthquakes. The new three-dimensional imaging extending to 50 kilometers or 31 miles reveals a deep system that reaches far below the shallow earthquakes experienced by residents. The possible primitive melt-rich zone, beginning around 25 kilometers or 15.5 miles, indicates that the roots of Campi Flegrei extend deep into the Earth's crust and upper mantle. Above it, the shallower anomaly, around 10 kilometers or 6 miles, may represent a pathway or storage region where magma can move through the crust. Closer to the surface, hydrothermal reservoirs and fractured rocks respond to pressure and fluid movement. The entire system is connected, but it does not behave as one simple chamber. That new picture may help explain why Campi Flegrei can remain active for so long without erupting. Magma and heat can be supplied from depth, while much of the pressure is accommodated through deformation, earthquakes, and fluid movement. Gases can escape through hydrothermal pathways. The crust can absorb some of the stress through fault movement. Magma can stall at different levels instead of reaching the surface. This creates a system capable of remaining in a prolonged state of unrest. It also creates a difficult forecasting problem because the transition from one state to another may depend on several processes occurring simultaneously. A volcano does not necessarily need a dramatic change in its entire plumbing system to produce a new eruption. A relatively localized pathway could potentially become important if pressure, permeability, and magma conditions align. Scientists are therefore monitoring both the broad system and the smallest changes within it.